All right. Good afternoon, everybody. Hopefully this is working now. As you may have noticed, I am not, in fact, Professor Hayonichi. I considered growing out the mustache a little bit more to make the case, but thought better of it. I'm a second-year graduate student instructor. I teach probably somewhere around a third of you guys in your discussion sections, and I will be covering for the actual professor of this course while he is at a conference in Washington, D.C., doing all manner of important chemistry-type things, I assume. So, as you may remember from last week now, we were talking about the actual three-dimensional structure of molecules, the way that we arrange bonds, non-bonding pairs, various pairs of electrons around any given atom that has some type of bonding around it. So as we start to talk about polymerization and the existence of larger scale systems, we can first take a look at the system for hexamethylene diamine. You'll notice that around every one of these carbons, we have a steric number of 4. Likewise, we have a steric number of 4 around nitrogens because we have 3 bonds and 1 non-bonding pair for every nitrogen. So as a result, we're going to get a structure that has, along the lines of this tetrahedral shape, bond angles of about 109.5 degrees, with some little bits of variation, but on average we should see something similar to just your usual tetrahedral shape. And we also have the molecule sebacoyl chloride, and around each one of these carbons, on the outside, we're going to have a steric number of 3. Because we only count the double bond once, so we have a total of 3 bonds, therefore we have a trigonal planar kind of shape with 120 degrees in between each bond. Now, as we continue discussing about this, we're going to be representing hexamethylene diamine with this angled zigzag kind of shape, and the sebacoyl chloride with this, I guess, curlier coil kind of shape. When we react these two molecules together, we actually get a repeating polymer. Because these nitrogens only want to react with this type of carbon, and this type of carbon only wants to react with nitrogen, we will necessarily get an alternating type of unit. Whereas usually we talk about molecules being very small, being composed of a small number of atoms. In the case of a polymer, polymers being things like nylon, like fibers, spider silk, proteins, all manner of things, we actually start talking about a larger scale kind of structure. So whereas we have these individual parts that have a fairly predictable type of shape, at the larger scale, the actual individual molecular connectivities start to matter a little bit less. We start talking about large scale types of structure, which is going to be more related to general types of shapes that are allowable, general kinds of what we call molecular topologies that are possible. So we have a demo where we're going to be adding these two molecules together. We can get the video up onto that. Maybe? There we go. It's over that direction, maybe. Okay, so I want to show the secret of how it's actually made. There we are. All right. So as you may notice, we're adding a couple of different molecules together. There's both different chemicals, which are composed on a smaller scale of molecules. Although really all you're seeing on that video screen right now is some glass. But I promise chemistry is happening. Yeah, see? There we go. As you might notice, we have this layer in between there where we're actually getting the formation of this polymer. These two chemicals are actually not able to mix with each other. So at the interface in between them, what we're actually getting is the formation of the polymer at the very beginning. And so the way that we would go about actually producing a fiber out of this is simply just by grabbing some of it and pulling it out, depending on how well it feels like behaving. Does it mean this work? So to some approximation, we can actually consider this as a single molecule. A whole bunch of smaller parts added together over and over and over again into one continuous string of a larger molecule. I keep on breaking this thing every time I try to do it. But regardless, as you can see, whereas usually we have bond lengths in molecules that are somewhere on the order of 10 to the minus 10 meters, we actually are clearly getting long strings of single molecules that are on the order. Yeah, I'm going to try to do this in a way that won't break it. See how coordinated I am? Right at the side, but again, this is clearly on the order of actual meters, rather than just being on the order of angstroms or nanometers, or something extremely small. All right, I need to break something if I don't do anything more than this, but here we go. All right, thank you. So as you can see, we're going to get a fiber kind of shape because we necessarily are only able to have these individual components, these monomers, form into a polymer by adding one at a time. So we can't actually have much in the way of branches of the structure. What we're able to have is long chains. And naturally the long chains will form chains that are actually long enough that we can actually see them with the naked eye. We can possibly spin these together, produce fibers we can then make clothes out of, so on and so forth. Now in a somewhat more familiar situation, we're talking about the polymerization of ethylene into polyethylene. Oftentimes these chemical names actually do make some sense. So we're looking at ethylene, a bunch of little guys like this, the double bond between the two carbons. And then we're going to polymerize this into polyethylene, where we have a whole bunch of CH2s all next to each other. So our question for our chem quiz, and it looks like we don't actually have chem quiz set up quite yet. Hopefully somebody can help me out with that momentarily. We're going to be looking at whether the bond angle is going to increase, stay the same, or decrease as we polymerize from ethylene to polyethylene. And maybe somebody will be able to come give me a hand and actually set this up to let you guys answer the questions. So enjoy your extra minute or so of time to think about the bond angle changing. Naturally, I would recommend you consider, well, you can't see it so much anymore, but if you could see it, think about what the steric number is going to be. Think about how that connectivity is going to change when you go from all these little ethylene monomers up into the polyethylene polymer. Hey, look, eye clicker's happening. All right. So, just want to go over this guy, right? And continue your thinking. And here we go. I'm going to cut down time a little bit so we don't have to wait quite as long. You got about a minute left. Advance a few forward, maybe. All right. So does that bond angle increase, stay the same, or decrease as we go from this double bonded ethylene into the multiple bonded polyethylene? Hey, we're over 400. We're beating the morning. 30. Enjoy your next 10 seconds. Maybe we can get up to above 450. Yeah. 49. Oh, come on, somebody else. All right, there we go. 450. Everybody wins. All right, so we'll see what this way looks like. All right, we have kind of a mix with a slight preference for a decrease in the bond angle, but a lot of people think it's going to increase. Some people want to say it's going to stay the same. So let's try this guy again. And take a minute, talk to people around you and try to figure out whether this bond angle is going to increase, decrease. I think those seem to be the main priorities. Make sure you think about what the steric number is going to be and how it's going to influence the possible shapes and therefore the bond angle. All right, I know there are 40 of you guys. Click in. All right, 5 seconds, come to a conclusion. 15 more of you guys. Maybe, not quite. All right. Barely 15 people got bored in between the two of those and left. These things happen. All right, looks like we have a general consensus that we do in fact have a decrease in the bond angle. I agree with you guys. So let's take a look at why that is. So we start out in the case of ethylene, we have a steric number of 3. If you recall, we don't tend to double count the double bond. We only count it once. So we have a total of 3 bonds to each one of these carbons, which gives us a steric number of 3, therefore a bond angle of 120 degrees, all this in the same plane. Now when we go into polyethylene, we end up with 4 bonds on every carbon. So naturally we have a steric number of 4. Steric number 4 implies we have a tetrahedral shape, and therefore we're going to have a bond angle of about 109.5 degrees. 109 is less than 120, and so yes, we do get a decrease in the bond angle with letter, I guess, C. Now we're also going to talk a little bit about different ways that we can form a molecule. With polymers, we have general large-scale kinds of shapes. We're going to have, in proteins, we have a primary structure with the series of amino acids, secondary structure in terms of helices and beta sheets and whatnot. We're starting to get at these smaller scales so that we easily understand what's happening with small molecules. At least that's a general preference for those of us who prefer physical chemistry over organic chemistry. So we're talking about the possible structural isomers. On the one hand, if we have 2 carbons, 1 oxygen, and 6 hydrogens, we can form ethanol by connecting things in this form, carbon, carbon, oxygen. Or alternatively, with the same number of carbons, same number of hydrogens, and same number of oxygens, we can form it carbon, oxygen, carbon. This first one up here is called ethanol. It is a popular component of numerous adult beverages you may have heard of. It's somewhat toxic, I guess, in the definition of what toxic means. If you ingest a bunch of it, you can experience acute alcohol intoxication, which at certain levels can be enjoyable. In the case of dimethyl ether, however, it's going to be a little bit less fun if you ingest it. And actually, usually you don't actually use dimethyl ether for a whole lot. We use diethyl ether. Causes perhaps a more severe intoxication and is also significantly poisonous. And at least in my personal and vaguely professional opinion, ethanol is a lot more enjoyable than ether is. I mean, I guess to each his own. But yeah, if you're underage, you shouldn't drink ethanol. It's not legal. If you're of any age, you shouldn't ingest a whole lot of ether. That's just a generally bad idea. And really, the difference is not that large. It's just moving this carbon 1 over instead. The slight difference in connectivity can make a big difference in terms of what this chemical will actually do to you. We can also talk about a somewhat more subtle type of isomerism. Rather than actually changing the way things are connected, we can have things connected in different places, a different overall geometric shape, different types of orientation. In the case of this dichloroethene, we can have the carbons double bond. We can have the chlorines on alternate sides. Call this the top, call this the bottom. We can have them both on the same side, both on top. Or we can actually have both of these chlorines attached to only one of these carbons. We tend to refer to this guy as cis dichloro, or I guess cis 1,2 dichloroethene. Cis means we have it on the same side. Trans is the opposite side. And exactly what the word is for here, it would be a different kind of name. But these, while they're not quite as dramatic of a difference as in the case of ethanol and dimethyl ether, we are going to find there's important physical and chemical differences. For example, if we look at the existence of a dipole moment from the difference in electronegativities, if we were to have these in a full solution, apply an electric field, we'd actually be able to measure how strong this dielectric constant is, which is related to the dipole moment, as we call it. You notice that in the case of the trans isomer, we have an asymmetry that actually any small-scale potential dipole moment will cancel out with something else of the opposite direction. However, in the case of the cis isomer, we end up with an overall arrow in this way, and in this situation, we're going to have an arrow going in this direction. So the way that we have things organized in space is going to be important. Just by having a bucket of atoms, we don't necessarily get certain chemicals. The way that we connect them is important, and the orientation in which we connect them is also going to be important. So in the case of pentane, we have the question of how many structural isomers. Remember that a structural isomer is like in the case of ethanol and dimethyl ether, where we actually have a different type of connectivity, a different order of connections. How many possible structural isomers can we have for pentane, which is 5 carbons and 12 hydrogens? So think to yourself, might be a good idea to draw some pictures. Try to think of how many possible ways we can organize pentane in non-identical pictures. Also note that because we don't really have a way to label a certain carbon in a certain way or a certain hydrogen in a certain way, we assume that if something can be rotated to be the same shape, then it is in fact the same shape. So just by drawing the exact same thing but rotated 90 degrees, that doesn't make it a new molecule. Otherwise, the answer would be an infinite number because every little tiny angle we could rotate it would get a new thing. some reason the first round of the question always gets all the people to answer. The second round, not so much. Come on, 450. Ah, all right, close. Oh, wait, there we go. And way to register it. All right, so we have apparently a pretty good mix. Some people think 3, some people think 5, a few people like to think 7. I think we need a little bit of time to talk to each other. And remember that you have to have the same number of carbons. You have to have 5 carbons, you have to have 12 hydrogens. And you need to be very careful in making sure that you don't accidentally double count the same structure. So talk to each other. You got another minute and a half. How many possible structural isomers do we have for pentane? All right, remaining 50 of you, you have 12 seconds. In general, the second one of these rounds of questions is going to be more valuable than the first round, so make sure you answer sometime in the next 2 seconds. Maybe, no. 11 people got lost. Let's see what our answers are looking like. Well, I guess it's not 7. You agree with that? And there's some uncertainty as to whether it's going to be A or B. I will tell you right now that, in fact, the actual answer is going to be A. And I will now explain why that is. So a shortcut here is to realize that we can't have any double bonds or any rings involved. As soon as we introduce a double bond, that means we have to lose 2 hydrogens. If we introduce a ring, we have to lose a couple of hydrogens. And since we have to make sure that we have 5 carbons and 12 hydrogens, neither of those can be an option. So really, the only way we can really differentiate things is going to be by looking at the longest unbranched part of the chain. So obviously, one choice is to have just 5 carbons in a row. We're, again, implicitly believing that those hydrogens are there. They would be attached. Just kind of like to get lazy sometimes. We're not actually going to draw every single one of them. The next possibility is we can have a chain of 4 with one coming outside of it. Note that if I counted from here 1, 2, 3, 4, or from here 1, 2, 3, 4, or 1, 2, 3, 4, I still only have a main chain length of 4. There has to be something else that is being branched off, no matter how I go about counting this. If I were to put the carbon over here instead, then just looking at it from the other direction would be the same thing. And then finally, a chain length of 3 with 2 branched off. Whether I look at the chain in the vertical direction with the branches on the left and right, or if I look in the horizontal chain with the branches up and down, I still only actually have 5, 4, or 3-membered chains. And this is the total number of possibilities. As soon as I try to go down to a 2-member chain, suddenly I'm going to be creating, on accident, actually a 4-member chain. So as a result, our answer is going to be 3 possible structural isomers of pentane. And now there is actually an even more subtle kind of isomerization. Now we have what is called enantiomers. They are chiral stereoisomers. So what we have is really one molecule that is the mirror image of another. For example, if I can get the video of this guy right here. All right. So as you may see, I have a nice looking molecule right here, and I have, in fact, a mirror. You can see in the mirror image what it would look like. Now watch as I pull it up. Hey, look at that. I actually have the mirror image in my other hand. If you see what the mirror would show me, it's the same thing as this. So we have what I hope you believe are perfect mirror images of each other. We have these 2 molecules that have some kind of difference. We know they're mirror images, but is there a way that I can actually rotate them around that I can make them look the same? And the answer is that I cannot, in fact. It's impossible for me to rotate these guys around in a way that would allow everything to line up exactly. If I line up so that the white ones are aligned and that the kind of orangish brown ones are aligned, then necessarily, sometimes things break. That would change the rules. But you see that I've got the kind of pink, purple, and green ones are mixed up. If I try to set it up another way so that I have, say, the white and the purple ones set up, then the brown and the green are mixed. You may have noticed something that is more familiar for the situation of talking about chirality. On average, people tend to have a pair of hands. I do. I don't want to say everyone does because there are, of course, some exceptions, but the vast majority of humans have a pair of hands that are effectively mirror images of each other. Yes, I am, in fact, somebody teaching you chemistry at Berkeley, and I am telling you, hey, guys, check out your hands. But really, I mean, have you guys looked at your hands? Like really, really look at them? Because they're cool. So they are, in fact, a mirror image of each other. I can do the same thing. Look at the mirror. Hey, look, my hands line up like that. But there's no way that I can actually get them to line up completely. If I try to go like this, okay, they line up pretty well, but now I have the back of one hand and the palm of the other one. There's no way that I can actually make my hands line up. This is going to be fundamental. This is why we actually take the word chirality, or chiral, from the Greek word for hands. I think it's chir. So what we end up having is actually that we can't separate these things out into one of the other possibilities. The same way that if you've taken, say, a physics class or math class, you can talk about the right-hand rule when you draw your axes. Using your left hand will give you a similar shape, but there will be something fundamentally wrong. You won't have a right-handed axis system because you use your left hand to do it. So things get kind of mixed up quickly.